Today our discussion is going to be on oxygen that we have started before. This is going to be the second lecture on oxygen. Before we just did oxygen and few compounds of those that are common, like oxides of some like nitrogen oxide or those sulfur. So today our discussion is going to be solely on peroxides, and the superoxides, also some hydroxides, and we are going to talk more about some non-metals oxides of oxygen, the way the electronegativity affects which oxide is going to be formed. And Said Latif is the presenter. So at the end of this lecture today, it is expected that we should be able to describe the general preparation, some properties and uses of some peroxides and hydroxides, and also some non-metallic compounds of oxygen. We are expected to be able to describe them out, how to prepare them, their properties and their uses, the way we have been doing before. Peroxide and superoxide. Let me just start from what is called the peroxide. When you have a metal in company of a non-metal, like when you have a sodium in company with oxygen, you can have a sodium oxide, like when you have one atom of sodium and oxygen reacting and together, you can have a sodium oxide. But in this case, a peroxide is a higher oxide of non-metal, like sodium 2 oxygen 2. Like in this case, when we have potassium 2 oxygen 2, it is different from just potassium oxide. This is called a peroxide when you have 2 at the bottom of oxygen and you have 2 at the subscript of the metal that combined with oxygen. This is a peroxide. This superoxide is when oxygen reacts with oxygen with an oxidation number of -2 reacts with metal. You have a superoxide, like we have in this case now. This one is different from oxide, because if it were to be oxide, it is going to be K2O, but in this case is K02. So something must tell us, must ring a bell in our head now. What is really responsible for this? Now, what is responsible for it in simple answer is the amount of oxygen that is available during this chemical reaction. If you have a higher number of oxygen, you have a peroxide. I mean, if you have a superoxide. If you have a moderate number of oxygen, I mean, if the amount of oxygen is comparable with the amount of metal that is reacting together, you're going to have a peroxide. But if the oxygen is far, as in excess of the metal that is reacting with it, we are going to have what is called a superoxide. In this case, a superoxide is contains a higher oxygen than peroxide. So from what we have taught and how to calculate the percentage of elements in a compound, I believe you should be able to ascertain this fact from it. So if you calculate the amount of oxygen here, it's going to be 32 over the total molecular weight of this multiplied by 100. Here it's going to be 32 over molecular weight of this. Obviously, oxygen is more here than here. So superoxide is formed when you have a higher oxygen than in peroxide. But all in all, high temperature is needed for this reaction to take place. So how are we disturbing ourselves with the study of peroxide and superoxide? It is because there are many uses in chemical industries. that this peroxide, like sodium peroxide, potassium peroxide, that are being put into. The first one is because of the high number of oxygen that we have in peroxide and superoxide. They are very, very important as oxidizers, and all of us, I believe, we know how important an oxidizer is. We have been talking about oxidizers and oxidation reaction. So all these peroxide, sodium peroxide, hydrogen peroxide, all these are very, very important as oxidizers in chemical industries, and they are also important in some other chemical processes. And apart from that, in medical practice, a disinfection, when somebody has a sore on his leg or somewhere around the body, to treat the bacteria that has been infested, or to prevent bacterial infestation on all those sores, they use disinfectant. These disinfectants, many of them are made from hydrogen peroxide, so that's another use. So in another use is in bleaching. When you have a stubborn stain on your clothes, you can use peroxide, any of the peroxide that are suitable, that will not destroy your fabric. You can use it as bleaching agent. So those are the few uses of peroxide and superoxide that we're going to talk about. So let's go to another concept, that is hydroxide. What is hydroxide? We have been talking about it: sodium hydroxide, potassium hydroxide, calcium hydroxide. What is really the hydroxide? The hydroxide is just the compound that contains hydroxyl ion. When you have any compound that contains hydroxyl ion, it is an hydroxide. Not just when you have oxygen and hydrogen standing with each other, that is called hydroxide. No. Like in water now, water is not an hydroxide because oxygen and hydrogen are also standing, but that doesn't make it an hydroxide. So when you have this hydroxyl ion, like we have it here now, reacting with let's say metal, then such compound is an hydroxide. It can be sodium hydroxide, can be calcium hydroxide, can be magnesium hydroxide. There are many hydroxides like that. Then how do we prepare them? We have two general methods on which we prepare the hydroxide. The number one depends on the method depends on the solubility. We want to prepare soluble hydroxide, or we want to prepare an insoluble hydroxide. You know what soluble hydroxide means, all those group 1 and group 2 hydroxide. Then something like aluminium, some group 2 elements like magnesiums, they are not really soluble like that. So soluble hydroxides are produced by the reaction of the metal with water, or sometimes use metal oxide with water. So why we are using metal oxide with water is to prevent the severity of the reaction, because like sodium now, the reaction with water is a very violent one. It's very, very dangerous and it's difficult to handle. So to be on the safer side, chemists decided to use metal oxide like sodium oxide. Now they react with water. The oxide will have coated the surface of the sodium and passivate it, so that the effect of blowing up or explosion might be reduced, or if not totally eliminated. That's why they're using sodium oxide, metal oxide. The second method is for insoluble hydroxide. How do you prepare insoluble hydroxide? Is when you have a solution of a soluble sort of that hydroxide you want to prepare. Then you now combine with hydroxide ion. How do you get hydroxide ion? Is when you have sodium hydroxide or potassium hydroxide, all these soluble hydroxide. So when you have them and you want to prepare aluminium hydroxide now, as an example, in magnesium hydroxide as an example. So magnesium hydroxide, what you just need is a magnesium salt, like magnesium chloride, like magnesium sulfate, like magnesium nitrate. When you have a magnesium salt soluble, that means you can use magnesium nitrate. So you have that. Then you now look for a solution that contains hydroxide, like sodium hydroxide. So there's going to be an exchange of ion. Like sodium will go to the ion of magnesium, magnesium will go to ion of sodium. Then in that case, one is soluble and one is not soluble. That is a double decomposition reaction. Since sodium is there, sodium will go to the nitrate of the magnesium to form sodium nitrate, which is very, very soluble in water. Then the magnesium will go to the hydroxide of sodium, that is magnesium hydroxide, that is not soluble in water. In that case, you can use filtration to separate the two of them based on the solubility. Then you take your hydroxide that is not soluble. The sodium nitrate, and I'm just using the sodium nitrate as an example. You can use potassium nitrate also. Potassium hydroxide also. Just make sure it is soluble hydroxide, then soluble salt of the metal you want to prepare it hydroxide. There are many reactions, like I've explained in the first the previous slide, that you can have metal reacting with oxygen to produce hydroxide if you want to produce the hydroxide. But there are times that you don't react metal with water to form hydroxide. Apart from the severity of the reaction, it depends on solubility, like I've explained. Like magnesium, now that is not soluble, you don't react magnesium with water, because you won't get the hydroxide, because magnesium is not that reactive with water. That is why we use another method for preparation of magnesium. Then the other one, I talk about how to passivate, or how to eliminate the severity of a reaction. That is when we use the oxide of the metal, then reacting with water to form hydroxide. That is, the oxygen will have passivated the surface of this, so as to prevent the explosion in these reactions. This is for insoluble. This is magnesium salt, magnesium nitrate, can be magnesium sulfate. This aluminium salt. This is a solution that contains the hydroxide, and it can be from anywhere, like I've explained. So this is what we are getting. So the other half of the reaction we are not interested in. That's why we didn't write it, because if it were to be nitrate and this were to be sodium nitrate, so we don't need it. That is why we didn't bother ourselves to write it. Care must be taken if we are doing this reaction to find to find the stoichiometric amount of each of this that is necessary to produce hydroxide. Because if we have excess hydroxide now, as in that is in excess of what this salt is able to take, then instead of forming the hydroxide, we are going to have after the hydroxide might have been formed, when you have excess hydroxide in the solution, then it's going to dissolve this and form these complexes. So we not even notice anything again, because everything will have dissolved in the water and formed this. So we end up with nothing. In order to do that, we need to calculate the necessary amount of hydroxide that is needed for this reaction to take place. How are they used? Industry use large quantities of sodium hydroxide as a cheap, strong base. Like in soap industry, detergent industry, they use sodium hydroxide when they are preparing their products. Then again, sodium hydroxide is employed in the production of other sodium compounds. Like in sodium chloride now, you can use sodium hydroxide to prepare it, and it's also used in neutralizing acidic solution. That is in industry. Apart from that, is the suspension of magnesium hydroxide constitute antacid make of magnesia. What we are trying to say is this: in medical practice, there are times that when somebody is suffering from ulcer, there are times that the person will be asked to use antacid. Or when you have something like allergic reaction in your throat or something like that, that is caused by acid, then magnesium hydroxide is always the demolition that is prescribed for suspension. So the person will take it and it's going to neutralize the acid in the alimentary canal of that person. That is one of the uses of hydroxide. Another one is the reaction of hydroxide with appropriate acid is used in preparing salt. If you want to prepare salt now, let's say prepare sodium chloride salt, now that is common salt, it's very, very common, we use it at home. You can react sodium hydroxide with hydrochloric acid. So that reaction is neutralization reaction. There is going to be exchange of iron and sodium will go to chlorine to form sodium chloride, and it's very, very useful. Yes, let us go to another aspect of this lecture, that is some non-metal that contains oxygen. Most of the non-metals react with oxygen to form non-metal oxide. So the electronegativity determines what is being formed. Is it going to be the oxygen of the non-metal or the non-metal oxide? I will explain what I mean later. Depending on the available oxidation state for the element, a variety of oxides might be formed. Like in this case now, this is nitrous oxide. This is nitric oxide. This is sulfide. This is sulfate. This is not fluoride. This is oxygen fluoride. That's what I mean by depending on the oxygen, the electronegativity values. Electronegativity value of oxygen here is more than that of nitrogen. So what we are getting here is something oxide. When you have electronegativity of oxygen more than the non-metal, what you are getting is oxide. But in this case, electronegativity of fluorine is more than oxygen. What you are getting is not a fluoride oxide. It is called oxygen fluoride. I don't know if you are getting what I'm trying to say here. The higher electronegativity is the name of that compound. If it's oxygen, it's going to be something oxide. If it's fluorine now, like in this OF2 now, it's going to be oxygen fluoride. That is what I'm saying. So now let's start from sulfur that contains oxygen. We have two common compounds that contain sulfur and oxygen. The first one is SO2, that is sulfur 4 oxide, that is sulfur dioxide. The other one is sulfur 6 oxide, because sulfur can act for oxidation number of 4 or 6. The odor of burning sulfur comes from sulfur dioxide. So when you have a sulfur, you burn it, you may not even know, but the odor you are perceiving that time is from sulfur dioxide, because oxygen might have reacted with this. So sulfur dioxide occurs in volcanic gases, because that is combustion, and it's in the atmosphere near industrial plants because of the sulfur that is emitted. So when the sulfur now gets, because sulfur is at higher temperature, now when it gets to the atmosphere, it reacts with oxygen. So when to form sulfur dioxide. So when we get close to that place or those industrial area, the odor we get also is sulfur oxide. Burning fuel containing sulfur compound. That is what I'm trying to say. When you have a sulfur compound, because in our fuel we have some amount of sulfur. If as the majority of the fuels in the world contains sulfur, not it's only few countries that don't have sulfur. So when you have combustion of fuel like that, maybe in the industrial plant or in the effluent of a vehicle, so there's the sulfur that is emitted into the atmosphere can react with oxygen to form sulfur dioxide, and that is the odor we are perceiving. So how do we prepare this? I said oxygen reacting with sulfur, that is sulfur oxide. So commercial production can be sulfur. You burn sulfur to form sulfur dioxide. So if you burn sulfur in oxygen, you form sulfur dioxide. So if you have excess amount of oxygen in sulfur, you form sulfur 6 oxide. That is as simple as that. Another one is the roasting of sulfide, like we have in this zinc sulfide, we have in iron sulfide, we have in copper sulfide. So if there is roasting, and roasting means burning something in oxygen. If you burn it, it's either you burn sulfur or you burn the compounds of sulfur. So if you burn this in oxygen, you're going to form zinc oxide, and sulfur is going to be deposited in where and the reaction is taking place. That's another way of doing that. But in the laboratory, this is not so suitable because the yield is small and the reaction needs a lot of it, which is not economical. So how do we do that? You can have a strong acid that contains this sulfide or this. When you have a strong acid, then reacting with what is it called? With a salt that contains sulfur. When you have a strong acid like H2SO4, HCl, that contains the sulfide salt, then you have sulfur oxide. H2SO3, that is another sulfur that contains this, is formed first, then slowly decomposes into this. What I'm trying to say is this: you have an acid, you have another compound, a sulfide salt, like sodium sulfide now. So you now react them together, then this one is going to form first. Then after, when the reaction is going on, this one is not stable, it's going to decompose. When it decomposes, it forms sulfur dioxide. That is what I want to explain in simple terms. It forms this and water. Sulfur dioxide also forms when many reducing agents react with hot concentrated sulfuric acid. Sulfuric acid is H2SO4. Reducing agent is to reduce the oxygen. In fact, you can even use the dehydration reaction to form this. So if you remove the element of water from this, you form sulfur dioxide. If you have a reducing agent like H2S now, H2S is a very strong reducing agent. It reduces H2SO4 to sulfur dioxide. Then for sulfur trioxide, when you have sulfur and oxygen that I've explained, if you react them for a long period of time so that the sulfur is in contact with more than enough amount of oxygen, you're going to have sulfur 6 oxide, because sulfur oxide will form first. Then when you have excess of oxygen, it oxidizes the sulfur 4 oxide to form sulfur 6 oxide. These are some of the properties. Sulfur dioxide is a gas at room temperature, and the SO2 molecule is bent. What I want to say is this: in SO2 molecule is like a V shape, like shape of water. The sulfur is sandwiched in between the two oxygen atoms. The melting point of sulfur trioxide is 17 degrees, and it boils at 43 degrees Celsius. What we're trying to say is this: at room temperature, we expect the sulfur trioxide to be something like a molten substance. So below 17 degrees, it's a solid. So in the vapor state of this, its molecule are single SO3 units. Yes, because of the intermolecular force between them. Because after 43, it boils, then it becomes vapor gas. So if each of them will become discrete particles. But in the solid state, it can exist in several polymeric forms depending on the state of sulfur. Halogen oxygen compounds. Halogens are group 7 elements, like chlorine, like fluorine, like iodine, like that. They have, especially that of chlorine, oxygen chlorine compound are very, very common. ClO2, ClO3 minus, ClO2 minus. They are very, very common. In fact, you can form acid from them, as we're going to see later. The halogens do not react directly with oxygen. I remember we said this when we were when we started introduction to this non-metal, chlorine do not react with oxygen, but are being produced when halogen react with oxygen containing compounds. So when we have the compounds that contain oxygen, like sodium oxide now, like sodium peroxide now, like hydrogen peroxide, so you react that with chlorine, you are going to form water, and this compound that contains oxygen and chlorine, it could be ClO2, it could be ClO3, it could be HClO. So depending on the amount of the hydrogen peroxide with respect to the halogen. Their oxides are extremely reactive and unstable, and their chemistry has little practical importance. So they are not that useful. That is why we don't really study these compounds, especially when they are not in company of other elements like hydrogen now. But if it were to be like with hydrogen, then that is also chlorate compound, acid, then they are useful. We are going to talk about that one later, but not today. So this oxygen halogen compound, so we have just only two. So let's just talk about them briefly. Dichlorine oxide and chlorine dioxide, I mean Cl2O and ClO2, they are just the only commercially important. These are used for bleaching agents. I mean, they are used for bleaching, especially in paper and pulp industry. Then for water treatment, because in the water, because we said they are not stable. So when you add this to inside water, it's going to decompose. Then the chlorine that we need in that water as a disinfectant, the chlorine will just be released, then do the work that we want it to do. That is what we have for today. I hope that you enjoyed the lecture. So before that, let us have revision of what we talked about. We said reactivity of metal with oxygen, and the amount of oxygen available dictate whether the peroxide or a superoxide will be formed. I've explained that one before. So it's going to be on reactivity, because if the metal is very, very reactive with oxygen, like in sodium, like in potassium now, then you now have higher amount of oxygen than, maybe we have two compounds now. Let's say we have sodium reacting with higher oxygen, then sodium we have a smaller amount of oxygen. So in the first one with higher oxygen we form superoxide, the second one with a smaller amount of oxygen we have sodium peroxide. So if the metal is not that reactive with oxygen, then they do not form peroxide like that. So peroxide and superoxide are useful, especially as oxidizing agents. Where this reactivity of metal with oxygen is also useful is in the production of hydroxide. That is when you have insoluble or not soluble. If it were to be a reactive oxide, then it forms hydroxide, soluble hydroxide. If it were not reactive, then it forms insoluble hydroxide. So hydroxide are formed from many routes. I've explained now. Example is the metal plus water. It could be metal oxide plus water. It could be reaction of a salt of that metal with a solution that contains hydroxide. There are many ways to form this. So they are useful in neutralization of acid because they are base. So when you neutralize acid, they form salt. Depending on the environment they are doing that. If it were to be in agriculture, then they reduce the acidity. Where we don't need the acidity, then we use them to reduce the acidity, especially in lime, slaking of lime. When you have slake lime, like that is sodium calcium hydroxide, in agriculture it is very, very useful. In our body system, when you have too much acid that is becoming problematic, then magnesium hydroxide is very, very useful in that. Magnesium hydroxide will convert the acid into harmless salt. Then their system will be free from acid. That is what we have for today. Thank you very much for listening. Next time is going to be on discussion of acids. Thank you very much for listening. God bless you.